Welcome to this Concept Explainer, brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. Today, we are starting a deep dive into a very, very important topic, Faraday's Law of Induction from Unit 6, electromagnetic induction. We promise to make this concept simple, easy to remember, and completely exam-safe for maximum marks. So let's just jump right in. We learned earlier that an electric current produces a magnetic field. That was a huge breakthrough. But the obvious next question is the reverse possible?
You mean, can a magnetic field produce an electric current?
Exactly. Can a moving magnet or even just a changing magnetic field produce a current in a wire without any battery?
That's a fascinating question because for so long, electricity and magnetism were seen as, well, completely separate forces.
They were. It took pioneers like Michael Faraday and Joseph Henry to prove they are actually two sides of the same coin. But here's a surprising fact to get us started.
Okay, I'm ready.
We all know generators work by spinning something, right? There's motion involved. But what if I told you you can have a coil and a magnet, both completely at rest and still induce a current?
Wait, how? If nothing is moving, how can there be any effect?
Imagine two coils just sitting next to each other. If you just vary the current in the first coil, say you turn it on and off, you will instantly produce an F in the second coil.
So just by changing a current somewhere else, you can create a current here. That feels almost like magic.
It does, doesn't it? But it's pure physics. And it shows that it's not the motion itself that's key, it's the change. We need to understand how this wait, what moment really works. So let's get to the core idea. At its simplest level, the idea is this. An F is produced in a conductor only when its magnetic environment changes with time.
Its magnetic environment. Okay, I have a doubt. What does that mean exactly? How do we measure that?
Very good question. That's where we introduce the concept of magnetic flux. Think of flux as a way of counting the total number of magnetic field lines passing through a certain area.
So more lines passing through means more flux.
Precisely. And the core idea of electromagnetic induction is that an F is created only if this magnetic flux, this count of field lines, changes. No change, no EMF. It's that simple. Let's use an analogy to make this stick. Think of electromagnetic induction like traffic police changing the traffic signal.
Okay.
The coil of wire is like the road.
Mm-hmm.
And the free charges, the electrons in the wire, are like the cars on that road.
Right. Cars on a road. Got it.
Now, if the traffic signal is steady, let's say it's green all the time, the traffic just flows steadily. Or if it's red, it's stopped. There's no sudden action. This is like a constant magnetic flux.
Okay, so a steady field means no change, no action.
Exactly. But what happens the moment the signal changes? From red to green or green to red?
There's a sudden movement, cars start rushing forward or they brake hard.
That sudden motion, that is your induced current. It is the change in the signal that creates the action, not the signal itself.
But that makes it so much clearer. It's the transition that matters.
And why is this concept so important? Because it is the absolute backbone of how we generate large-scale electricity. Every power plant, whether it's hydro, thermal, or nuclear, uses this principle to convert mechanical energy spinning a turbine into the electrical energy that powers our world. Let's build a mental image for this. Picture invisible magnetic ropes. These are the field lines, threading through a loop of wire.
Invisible ropes, okay.
For a current to flow, these ropes have to somehow tug the charges along the wire.
And how do they tug them?
They tug them only when the number of ropes passing through the loop changes. If you suddenly push more ropes through or pull some out, that change creates a force, a tug on the charges making them move. That's your current.
So if the ropes are just passing through steadily, even if there are many of them, there's no tug.
No tug at all. So now answer this for me. If I keep a magnet steady, but I just shake or tilt the wire loop, will the ropes still tug the charges?
Yes. Because by tilting the loop, I'm changing the number of ropes that are actually passing through it at any given moment. So the flux is changing.
Perfect. You've understood the core concept. It's all about that relative change. Now let's connect this to the formal insert wording, the language you need for your exams. First, we have to formally define magnetic flux. It's written as phi b equals b dot a, or BA cos theta.
Where B is the magnetic field strength, A is the area of the loop, and theta is the angle between them.
Exactly. That cos theta part is what accounts for the tilting you just mentioned. Now, could you please read the law as it's stated in the textbook? The exact words are important.
Of course. It says, the magnitude of the induced EMF in a circuit is equal to the time rate of change of magnetic flux through the circuit.
Thank you. And mathematically, we write this as epsilon equals minus d phi high b by dt. And for a coil with n turns, which is very common, it becomes
Epsilon equals minus n times d phi b by dt. You have to remember the n.
You must. But that equation can look a bit intimidating, that d by dt part and the negative sign. What does time rate of change really mean in simple words?
Yes, that's what I wanted to ask. And what is that minus sign doing there?
Let's break it down in steps. Step 1. The time rate of change, the ddt part, just means how fast the flux is changing.
So changing the flux in 1 second is different from changing it over 1 minute.
Drastically different.
Yep.
A faster change, a more rapid change in flux, produces a much larger induced EMF. That's why generators are spun very, very fast.
Just that's step 1. What's next?
Step 2 is the negative sign. This is probably the most crucial part. The negative sign represents Lenz's law. It tells us about the direction of the induced current. And what it says is that the induced current will always flow in a direction that opposes the very change that produced it.
It fights back against the change.
It fights back. Nature dislikes sudden change. If you try to increase the flux, the induced current will create its own magnetic field to decrease it. If you try to decrease the flux, it will create a field to boost it back up.
So it's always trying to maintain the status quo.
That is the perfect way to put it. It's all about conservation of energy.
Yeah.
You can't get electrical energy for free. You have to do work against this opposition. And step 3 is just remembering the n, the number of turns, which acts as a multiplier for the whole effect. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com. Let's quickly do a simple numerical example to lock this in. Imagine a coil with 200 turns, so n is 200. The magnetic flux through each turn changes from 0.02 Weber down to 0, and this happens in 0.1 seconds.
Okay, so n is 200, the change in flux delta phi is 0.02, and the time delta t is 0.1 seconds.
So we calculate the magnitude. Epsilon is n times delta phi divided by delta t, so that's 200 multiplied by
0.02 divided by 0.1, which is 0.2. So 200 times 0.2, that's 40 volts.
40 volts, see? And notice how powerful n is. Without those 200 turns, the voltage would have been just 0.2 volts. The multiple turns amplify the effect. This principle is what leads us directly to understanding the AC generator, which is a major application we study next. All right, now for a very important section, the silent killers. These are the common misconceptions that cost students marks.
Oh, this is important.
Misconception number 1. The wrong idea is that just having a strong, steady magnet near a wire is enough to make current flow.
I can see why someone would think that. Stronger magnet, stronger effect.
But the correct idea, as we've discussed, is that only a changing magnetic flux induces an EMF. A steady field does nothing. So the hook to remember is no change in flux, no current in the circuit.
Got it. No change, no current.
Misconception 2. The wrong idea is thinking the induced EMF only depends on the start and end values of the flux, ignoring how long it took.
They forget about the dt in the denominator.
They forget the dt. The correct idea is that the rate of change is everything. A slow change gives a tiny EMF. So our hook for this one is no hurry in flux, no high voltage.
I like that one. No hurry, no high voltage.
And the third, most tricky one, is about Lenz's law. The wrong idea is that the induced current always opposes the original magnetic field.
But the word is opposes, so that's confusing.
It is. The correct idea is that the induced current opposes the change in flux. This is a subtle but vital difference. If flux is decreasing, the induced current will create a field in the same direction as the original field to try and stop the decrease.
Ah, so it helps the original field in that case. It's always opposing the action of change, not necessarily the field itself.
You have it perfectly. The hook is oppose the change, not the field. Now, to make sure all of this stays in your memory, let's use some memory anchors. For the main relationship, use this mnemonic. Faraday says, fast flux flip, big EMF.
Fast flux flip, big EMF. Simple.
For Lenz's law and that negative sign, think of this phrase, nature dislikes sudden change and pushes back. It reminds you that there's always resistance to the action.
Nature pushes back. That's a great way to remember the opposition.
And a physical anchor. When you're studying AC generators, physically rotate your wrist like you're turning a crank. That motion will connect the idea of mechanical movement being converted into voltage in your mind. So let's summarize this entire concept in 3 key exam-safe facts. 1. The fundamental law. Faraday's law states that the induced EMF is equal to the time rate of change of magnetic flux. The rate is key. 2. Lenz's law. This gives the direction. The induced current creates a field that opposes the change in magnetic flux that produced it. This is because of conservation of energy. And 3. The application. This principle is the basis for motional EMF, and most importantly, it's the core working principle of the AC generator, which converts mechanical energy into the electrical energy we use every day. To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit profsam.com.
That is PROF Sam, right?
Yes, PROSSAM.com. Keep revising, keep learning, and we'll meet in the next deep dive.